Hello everyone. Let's continue the discussion on threshold voltage. So we have given a positive VSB over here, and this particular VSB is 0. And on the application of the gate to source voltage, what happens? Let's try to look into that. So while we increase the gate to source voltage in both the scenarios, try to observe this area and this area simultaneously. Okay, so when we increase the gate to source voltage, your depletion width increases on either cases. Your depletion layer width further increases on either cases. Okay, but there is one unique thing that happens over here is this one. So once you see the depletion layer width being increased in this particular area, it actually means that there is an accumulation of negative charges being expected over here. The accumulation of negative charges happens over here, and it's also expected at this point. Okay, so but what happens in this area, due to this particular terminal being connected to the positive potential, this attracts most of the negatively charged particles which is present over here. It attracts over here, and there is a small amount of VSP currents. We'll talk about the currents in a separate section. So once you see this particular terminal being connected to the positive potential of the battery, it attracts the negatively charged particles which is getting accumulated over here. But over here it doesn't happen. It just gets accumulated over here because this potential is at 0, and the VSB completely as a whole is at 0. Okay, so this is the second most important observation, that due to the positive VSB, the charges which is present in the channel are getting pulled towards the source area. Okay, and that doesn't happen over here. So logically speaking, what can go wrong? Let's see what will go wrong in this particular scenario. So this is trying to create the channel, but the positive source is not allowing it to do it, whereas over here that's not the case. As a result of that, if you see the voltage at which surface inversion happens over here is at a lower gate to source voltage. Let's observe that. So if you see, when you further increase the gate to source voltage, this area is almost inverted, but this area is not. If you see, there is a slant over here, it goes in ascending order. So this area is not yet converted to there is no surface inversion yet happened over here, but there is a surface inversion already happened at some gate to source potential. And that gate to source potential, we call it as VT in the previous case. In the absence of VSB, let's call it as VT0, VTO. So basically we'll try to define VTO as the threshold voltage at which the semiconductor surface inversion happens in the absence of VSB, whenever VSB is 0. But when VSB is at some positive potential, you still don't have the surface inversion happening. So it will take some more gate to source potential to make this particular area completely inverted to an N type. So let's try to increase the gate to source potential even more. Okay, we'll increase the VGS voltage over here. We'll try to increase the gate to source voltage even more, and then finally at some potential which is VTO plus V1. So there is an extra potential V1 needed for the surface inversion to happen in this scenario, and that purely because of the positive VSB value. Okay, so now we have two different equations to manage over here. At VGS equal to VTO, you see a surface inversion happening over here at VSB equal to 0, and at VGS equal to VTO plus 1, there is a surface inversion happening in this case. So we have two different equations over here, and these are all standard. The equation, the value of the VTO is, these are basically a function of the device parameters. Okay, I'll come to the equation of VTO and threshold voltage as well. So the conclusion is, in the presence of substrate bias VSB, we need an additional potential for the strong inversion. Okay, and the logical, if you see, that's pretty much the case. That's pretty much the case that happens over here, and that is needed. Okay, so we'll have the threshold voltage equation will be VT. The threshold voltage equation will be VTO plus you see this huge equation that's basically that has got a dependence on the technology parameters or on the device parameters. For example, the doping concentration of the p substrate, the n plus doping concentration, the n plus concentration over here, and so on. So this has got dependency over there. Okay, so it says that your threshold voltage is VTO, which is the voltage at which your surface inversion happens in the absence of VSB, plus you need some extra potential in the presence of VSB. So if VSB is 0, this particular term just vanishes off, and you have VT equal to VTO. But if you have VSB to some positive value or some value, you need this extra potential to achieve the threshold voltage. Okay, so that's pretty much it. And if you see, the VTO is the threshold voltage at which VSB equal to 0, and it's a function of the technology parameters. So I'll come to the VTO equation in some time from now. And gamma is referred to as body effect coefficient. So this equation, this additional term, came because of the body effect. That's basically the effect of the body terminal. So we call it as body effect coefficient, and it is represented in it basically expresses the impact of VSB. Okay. And phi f is the Fermi potential. This will cover it in a separate semiconductor device physics slide, so give it some time. For now, just consider this as some potential that is needed for the threshold voltage equation. We'll come back to the Fermi potential in a separate set where we'll be talking about only semiconductor device physics. So we'll come to phi f Fermi potential. It's a very interesting concept over here, but that will need some more device physics concept. So let's keep it for now, and let's call it as some potential which is needed for the threshold voltage equation completion. So when we have this particular things, let's say VT, this is the threshold voltage equation. Okay, and all these parameters, VTO, gamma, and the Fermi potential, VSB, these values are all constant, not the VSB, but the other ones are all constant, and that comes from a foundry. And these constants are basically nothing but your models. These models are being fed to a SPICE simulation, and this equation will now represent this particular MOSFET device. So that's why we need these particular values. We need the value of VTO, we need the value of gamma, and this we don't derive on the fly, but we need these values from the foundry. For example, let's look into one such case. The gamma is a function of 2q Na epsilon Si and oxide capacitance, where your epsilon Si is the relative permeability, which is again a constant. Your Na is the doping concentration, which again comes from the foundry. Your Q is the charge of electron, which is again a constant. This is the oxide capacitance, basically the capacitance which is present over here. And for this, you need the oxide thickness and all those things, which are again technology constant. They are all fabrication parameters that you see over here. And these values are all being fed to your SPICE simulator. And what does this say is, once you give these values, you will have the SPICE tool will derive the threshold voltage out of these values, and that threshold voltage will represent this device, will represent this NMOS. And also you have the Fermi potential as negative of phi t into natural log of Na upon Ns. So these are all the doping. The Ni is the intrinsic doping parameter of the substrate. So these are all constants, and constants are basically coming from your technology, coming from the foundry. So what we'll do is we'll keep this particular equation on a side note, and we will be coming back to this equation when we try to do this SPICE simulation, and we'll see how do we feed these equations or these parameters to the SPICE simulator to get an ID and VD characteristics of this NMOS. Okay, so this was about the behavior of the NMOS below threshold. Now what happens when we go above? Now since we have reached the threshold voltage, now what happens when we reach above threshold, and what happens when we apply some potential at the drain to source voltage? So that's a different region of operation, and that's what we call it as resistive operation. So let's try to look into the resistive operation of the NMOS in the next video. Thank you.